Hello everybody, and welcome to Embedded ARM Dev. In this video, I'm going to give you an introduction to shared libraries. We'll talk about how to create a shared library and how to link with a shared library when compiling. So what is a library? A library is simply a collection of objects that are made available for use by other programs. In general, there are two types of libraries, static libraries and shared libraries. In this video, we'll be discussing shared libraries. Also, be sure to check out my other video on static libraries. A shared library is a shared object that can be linked in by a dynamic linker when the process is loaded into memory. The library exists on the target device and is loaded one time into shared memory. All of the programs that need functions that are in the shared library are linked to those functions in shared memory. One advantage of shared libraries is that any changes to a shared library do not require recompilation of programs that link into it. The new .so file needs to be distributed, but binaries that link into it do not need to be recompiled. One disadvantage of shared libraries is that the shared object has to reside on the target platform for dynamically linked binaries to execute. Shared libraries should be compiled as position-independent code. Compiling as position-independent code allows the binary to be loaded at any address in memory without needing any modifications. With position-independent code, all dynamic symbols are stored in a global offset table. The global offset table contains entries for functions that will be dynamically linked. When the process is started, the dynamic loader resolves the global offset table entries to their addresses. In the binary, any reference to one of those functions will point to its entry in the global offset table, and that entry will point to the resolved address of the function. When compiling for position-independent code, GCC offers two pick options. There's the one specified the lowercase PIC and the one specified by the uppercase PIC. With lowercase pick option, the compiler usually generates smaller and faster code, but there may be machine-specific size limitations on the size of the global offset table in the code itself. When using this option, if the resulting global offset table will exceed this limit, the compiler will throw an error. For this reason, it is recommended to try to compile with this option first, and if the compiler complains, use the other type, which is the uppercase PIC. With the uppercase PIC, there's no size limit on the global offset table. This option will always work, but may generate code that isn't as small and fast as with the other option. For predictable results, it's best to use the same option for all stages of the compilation process. The naming of shared libraries on Linux generally follows a standard convention. Generally, a shared library can have three types of names: the real name, the shared object name, and the linker name. The real name is the name of the actual compiled shared object. It follows the standard convention of starting with lib, followed by the name of the library, followed by .so, followed by the major version, the minor version, and sometimes a patch or increment version. For example, the JPEG shared library, the real name is libjpeg.so.8.2.2. This indicates a major version 8, a minor version 2, and an increment or patch version of 2 for this particular shared library. Although many shared libraries follow this pattern, some do not, such as standard libraries like libc and libm. In those cases, the version information comes before the SO extension. An example of libc, you have libc tac 2.31.so. The second type of name is the shared object name, or SO name. A shared library will often have an SO name. It is not required, but it makes resolving version dependency much simpler. The SO name is essentially a label for a major version of a shared library that's used to help resolve shared library dependencies. A binary that is linked to a shared library with an SO name will look first for the SO name on the target system. On the target system, the SO name is usually a symbolic link that points to the real name of the current version of that shared library. We will see an example of this when we do the practical demonstration. For example, for the JPEG library, the real name has version 8.2.2, but the SO name would be libjpeg.so.8, indicating the major version 8. On the Linux operating system, libjpeg.so.8 would simply be a symbolic link that points to the real name, so.8.2.2. The third name is just the linker name. This is the name of the shared library that is invoked when linking the shared library in at compile time. GCC will look for this library during the linker phase when given the lowercase l option. To create a shared library, first compile all the source code into position-independent code modules using the desired pick option. Don't forget to use the lowercase c option, which creates the object files but does not link them. The next step is to compile the modules into a shared library using the shared option. If a so name is desired, pass in the option uppercase W, lowercase l, followed by the option so name, followed by the name of the so name you wish to give the shared library. You may notice that when compiling with either of the pick options, or when compiling without specifying either one, that they sometimes result in the exact same file output. Despite this, it's best practice to include either one of the pick options when compiling for shared libraries. Okay, so now we'll do some practical demonstrations to show how to create and compile shared libraries and compile binaries that link into them. Okay, so right now I'm on my Ubuntu VM and I've created a simple project that I can use to demonstrate how to create shared libraries. Now, this is exactly the same project as I did for static libraries, but instead of compiling for static, we're just going to compile it into a shared library and use it. If you watch my static library video, then this should be very familiar. So first, let's go over what's inside this directory. So we've got the do math. So this is the actual executable binary that we're going to run. Okay. So before we look at that, let's we'll look at add numbers. This is just the function add numbers, and this will be compiled into a single object file. And then we have sub numbers, and this is just the subtract numbers one. So this takes two arguments and subtracts them. So if you watch my static library video, then that seems familiar. And then we have the, before we do that, so I've got two directories here. There's include and lib. Lib has nothing in it right now. Include has the header file. So if I show you this, okay, so this just has the prototypes for those two functions that are going to be inside our shared library. So if you want to use any of these functions that are in the shared library, you have to include this. This prototype, this header file, into any of the code that needs it, so that it knows what functions are available in the shared library. Okay. So next, let's take a look at the actual source file. Okay. So if you watch my video on static libraries, then this is exactly the same thing. Okay. This is exactly the same file. So here, this is where we include the header file that has the shared library prototypes in it. And then this area of code here just gets us two pseudo-random numbers that we can use to pass into add numbers and sub numbers. Okay, so add numbers and sub numbers are functions that are defined inside the shared library, and the prototypes are given to us in this include file here. So all it does is generates two random numbers. It calls add numbers and passes those in, and then prints it, and then it passes the same two numbers to sub numbers. And that's it. So the first thing we're going to do is we're going to compile the objects using the fpick option. So I'm going to use the lowercase pick. Generally, it's a good idea to use this option unless the compiler complains and says that there isn't enough space or the global offset table is too large. Now we're going to compile the add numbers and the sub numbers. And also, let's not forget the lowercase c option. Okay, what this does is tells the compiler to compile these source files into object code, but not to link them, not to run the linker. Okay, so those will result in two object files. Okay, so we see here we got add numbers object file, and we've got sub numbers object file. So if we look at these, we can see they're both 64-bit relocatables, x86. So the next thing we're going to do is compile these into a shared library. So we use GCC, and we're going to say the output is going to be called libmath, and we're going to call it version so so.1.2.3. Why not? And so what we want to do here is put the object files in here. Okay, and we'll pass it the shared option. So this is what's actually going to give it the shared library. This is what's going to create a .so. Okay, and then also we want to pass in, I'm going to give it uppercase O. Okay, I'm going to give it a so name. I'm going to call it libmath.so.1. So this is going to be the shared object name, okay, which indicates the major version. All right, so here we go, libmath.so.123. So if we want to see this, if we want to see the SO name, we can use readelf and pass it the A option, which outputs everything. And we'll call that on the newly compiled library. And we'll pipe it to grep and search for so name. So we can see here that it's got this so name that we gave it. The next thing we need to do is we want to actually move this into the lib directory. So normally the shared object files have to be in a standard directory, like lib or user lib. We're just going to keep it local in the local lib directory, and we'll pass in an option to the linker, the runtime linker, which will resolve it for us. So move that into lib. All right, so now cd in here, and we see that we have this shared object right in here. Okay, so the next thing I want to do is we're going to create a symbolic link with the so name that links to this library that we've got here. So the ln command creates a link. The s is symbolic. Okay, we pass in the source file, and then I'm going to give it so.1. So this should be the so name. Okay, so we list this. We see that libmath.so.1. If we do file on it, it says it's a symbolic link to libmath.so.1.2.3. Okay, so this is what we want. So we'll go ahead and cd up into the other directory. Okay, so one thing we forgot to do was we forgot to specify, so if we go in here into lib, and we see that we have the two file names, right? We have the real file for the shared object, which this is the actual shared object binary, and then we have the SO name, which is a symbolic link that points to the real name. But there was a third name called the linker name, and so when we try to compile, so let me go back up here, GCC, okay, I'm going to compile do math, and I'm going to link into math, specify the capital I for include, L for lib. Okay, so this will probably fail because it's looking for math libmath.so. So when I do this, it says it can't find lmath. Okay, and that's because in lib we don't have the name, the linker name. It's looking for libmath.so, and that doesn't exist. So the easiest way around this is just to create another symbolic link. Okay, so we'll create link symbolic. We'll point it to the first symbolic link, and then we'll give it symbolic link name will just be the linker name. Okay, so now we have all three. So we have libmath.so. Okay, libmath.so points to libmath.so.1. libmath.so.1 points to the actual real name, and then the real name is right here. Okay, so now we should be able to compile. So we'll say do math.c output. Okay, and we're going to link into math. So now this should find the right, or actually before we do this, let's go ahead and move up a directory. Okay, so we're going to call GCC, that's the source file, output file, do math, link with the math. This is our custom shared library. Okay, now since our include file, our header file, is in a local include directory, we have to make sure we specify it using the capital I option, which specifies non-standard include directories. Okay, so the name of the local directory is called include, and then the same thing for the libraries. Okay, Since our shared library is in the lib directory, a local one, it's a non-standard directory, so we need to specify where that is. So the tag L should give us that. Okay, so we've got GCC, this is the source, output is do math, linking it with math, specifying the include directory, and specifying the linker directory. So this should work. Okay, so now we have do math. So if I do readelf on do math, not readelf, let's do file first. So we'll do file, do math. See here that it is dynamically linked. Okay. Now it does say a shared object. That's because the default on GCC Linux is now to compile all executables as a position independent executable. And so the file command interprets that as a shared object. But this is an executable. Okay. So it's important to know here that it's dynamically linked. So now what we'll do is we'll use readelf, pass it the A option to dump everything, all options for readelf. We'll call it on do math, and then we're going to pipe it to grep and look for shared. So this will list any of the shared libraries that this binary depends on. So we can see here that obviously it depends on libc because we had print statements in there and some other things like time and sran, ran, stuff like that. The other one is depends on is this libmath. This is the one that we've created. This is a shared library we've created. So you notice here that even though we linked to math, it linked to that shared library, but the SO name, so it actually is going to look for this SO name right here on the target system, which is what we want. Okay. Okay, so now if we try to run this, we're actually going to get an error. And we'll talk about why. So if I run this, it's giving us this error, cannot open shared object file, no such file or directory. So the reason is when the loader loads this program, it sees that it has a shared dependency for this, for libmath.so.1, and so it searches the standard directories for this particular shared name, shared object. Now, since our binaries, our shared objects, are in the local directory, the loader's not finding them. Okay, so all we have to do is change an environment variable and pass that to the loader so that when the loader loads this program and looks for that shared library, it will also look in that directory that we specify, and it should find our shared library. Now another option, okay, would be to actually move these to one of the standard directories like /lib or /lib. So if we go here, okay, so this is where most of the libraries are on this system. You can see them all in here. Okay, but when you're developing a new library, you probably don't want to do that. You probably want to test it locally first to make sure everything works correctly. And so the easiest way to do that is to specify an environment variable. So the variable that we want to use is called LD. So I'm sorry, we're going to echo this LD library path. Did I spell it right? So this probably is empty. Okay, and it is. So what we have to do is we have to pass this directory here. We have to add that, append it to this right here. So the normal way to do that, to append paths, you specify, so you set the variable. This is pretty standard in Linux shell setting environment variables. You set the variable equal to, you specify the new, so we're going to say /home/dev projects shared example lib, and you pass a colon to separate it, and then you give it the current value. Not that. Okay, library path. So what this does is prepends. It'll prepend this path right here to the LD, what the already existing LD library path. You can also put this first if you want, like right here. It doesn't really matter, but this I've seen this a lot. People, they'll prepend it instead of appending it. Okay. So another thing we have to do is, when we do this, we'll see that it has this path on here that we want. Okay, but the problem is if we call the program, this variable, this environment variable does not get passed to the next process that starts from the shell unless we export it. So all we have to do is call export, and then we'll do ld library path. Okay, so now it's exported. So when we export an environment variable, it makes it available to any child processes that the shell calls. Okay, so now we should be able to run, and it did run. Okay, now normally we would not have to mess with this. Like if you were compiling this for a target system or something like that, you probably wouldn't necessarily do this library path stuff here. You probably would just move these. You would just move these into the the lib directory, either the lib or user lib or one of the subdirectories in there. So we're gonna go look at that real quick. So I'm going to change the lib, and I'm going to go into x86. This is where all the libraries are. Okay, so I'm going to look for libc. Okay, so we see here that we got libc.so, libc.so6, libc dash. Sorry. Okay, so this is the actual so file. This so.6 is a soft link pointing to this one. Now, this is what I wanted to show you. So, if we were to look at this libc, well, first of all, let's call file on it. So, in our project directory, so we had this libmath.so was just a symbolic link that pointed to this, and then that was just a symbolic link that pointed to this. Okay, so that's fine. You can do that. Another way you can do it is to use what's called the linker script. Okay, and that's what this libc.so is right here. So if we were to just take a look at that in gedit, we'll just take a look at it. So this is a linker script. So I'm not going to go into too much detail, but this is what allows us to link into libc instead of having to specify libc.so. Okay, so this group command is basically just saying, hey, first check this libc.so.6, and if you can't find the function that you're looking for, then look in this one, which is the libc, the non-shared, the static library, and then you can, as needed means use this if necessary, and this is the actual linker file, so you only would use this as needed by the linker. Okay, so this is kind of this right here is kind of the critical part of it. So when we link into libc, it's actually reading this script right here and saying, hey, you're going to look for so.6, or you're going to look for this right here. Okay, all right. So I may do a video later that talks a little bit more about doing linker scripts because it's a big topic, and there's lots of there's a lot to it, so I don't want to get too much into it in this video. So the method that we used for our project worked just fine. Okay, so another thing I want to show you was, so I'm back here in my shared example, and we've compiled this do math. Okay, so it works for us. All right. Now, when we go into the lib directory, remember we had to create this soft link right here. I'm sorry, symbolic link right here. This libmath.so into here. Okay, this was just for the linker at compile time. So if we go back up to and we do redelf on do math. Okay, we see here that what it's actually going to look for is this so name that we specified. Okay, so this is what it's going to look for. So we actually don't need this on the target system. We don't need this at all. So I can just remove that, okay, and then do math will still run. That's because the loader is actually looking for this one, which does exist. Okay. Another thing I want to show you is how easy it is to update a shared library. So let's say we make some changes to our shared library and we want to distribute those. Okay. So I'm going to go ahead and recompile this. I'm not going to make any changes, but I'm going to give it a new version. Okay. So we're going to call GCC, and this is going to be called libmath.so.1.3.1, 3.0. We'll call it 130. Okay. And then we're going to pass it add numbers, subnumbers.o, give it the fpic command, and then we're going to give it the shared option, and then the uppercase L and the M. So what this does is pass a comma separated list of arguments to the linker. Okay, so these arguments here are for the linker. So now we're going to give this a so name of the exact same thing. It's going to be libmath.so.1. So we'll just compile this. Okay, so now we have this new libmath here, this updated version. Okay, notionally updated. So now what I'm going to do is move that into lib. Okay, so now we'll go into lib. Okay, and you'll see here that this so.1 points to 1, 2, 3. So all we have to do is remove that, and then we'll recreate it. Okay, so it's going to point to 130 now, and we're still going to call it so.1. Okay, so now what we have is, so this is the old version, this 1, 2, 3, and libmath.so.1 now points to 130, which is presumably the updated version. Okay, so when we go back up here and run do math, it's still going to look for this so.1, but now it's going to use this new updated library here, and it still works. Okay, now we didn't make any changes, but if we changed the behavior, then you would actually see that working. Okay, and so that's how libraries, that's how shared libraries are very useful, because we did not have to recompile do math. Okay, so you as a developer for the shared object, the shared library, you could make an update and distribute it, and those people that compile into it would not have to recompile their program. It would just work. Now, if your changes make it so that it's not backwards compatible, then you would actually need to increment this major version. Okay, and then you would need to make another link like so.2 and link it to libmath so.2.1.0 or whatever. Okay, so this works so long as you don't make any backwards incompatible changes. If you do make backwards incompatible changes, then you need to increment this major version and create a symbolic link accordingly. Okay, so if you want to support two separate major versions, you have to have both of them on, and you need to have symbolic links with the so name that point to the correct versions if you want to support both of them. Okay, so that's it for the practical demonstration of shared libraries. Okay, let's summarize what we talked about in this video. First, we talked about the definition and uses of the shared libraries. Then we talked about compiling shared libraries as position-independent code and the differences between the two pick options. We discussed shared library naming conventions, and then we discussed procedures for creating, compiling, and linking to shared libraries. Okay, that's it for this video. I hope you found it useful. Please leave any questions or comments, and we'll see you in the next video.